Hi, I'm Andre, and today we discuss the paper called Practical Lossless Compression. So we do losslessly compress data without losing anything with latent variables using beads-back coding. Now I have to say that what got me interested was that this scheme of compression beads-back coding is something that I've never seen before. And it took me a while to get my head around it. Now I understand it and I want to explain it to the world. So this paper was published in 2019 at ICLR, and it was published by James Townsend, Thomas Bird, and David Barber. Now, I'm currently doing an internship in doing research in lossless data compression, and this paper is one of those things that people seem to know, and I was curious and I got to read about it. Fun fact, I happened to study at UCL before, but let's get into it. So in this paper, they talk about how to losslessly compress data, and we'll do that with some latent variables and with this coding, but like what does compression actually mean? So we'll talk about compressing images in themselves. So we will going to have an image and we compress. Now, the pipeline for compression is that you have a sequence of symbols. So you have a symbol, you have a sequence of them. So let's say that you have n symbols. Then you are going to create a code from these, and then you will create a binary string that you will send to the other party. Now the other party will take this binary string, will create back this coding, right? This coding can be, for example, a natural number. So you will take your image and you will compress it into a natural number, let's say. Then the receiver is going to get back this natural number. And now here you use, in a way, let's say a proprietary coding scheme, a set of conventions that you have declared with the other party that you will both use. So one of those things is called ANS. You don't need to know any of the details. The point being, given a sequence, so it's a sequence of symbols, you get a code that then you can send, and then the other party can use the exactly same coding, the reverse part, to get back the exact set of symbols. And now, so this bit is deterministic to get from a symbol to encode it using INS, and then from this one to that one is deterministic. There is nothing sort of, in a way, probabilistic here. But now the big question is, how do you get a sequence of symbols and to create the code? Because if you think of the most basic code ever, it would be, let's say that these are the pixel values. It would be something like put a 5, then maybe put a bar, put a 7, put a 9, put a 21. This is a very basic code, but it has a big length. So what you want to do is that you want to, optimize from that. You want to use as few bits as possible. So if the output is a natural number, we want to take images, map them to natural numbers that are very small, meaning a small natural number requires very few bits. So if we get to map images to natural numbers that are small, then they are going to use bits. But not all natural numbers are equally probable. And this means that the images which are more probable, so the things that we will send more often, for example, meme images, we want to give them numbers that require fewer bits. The question is why? Because we'll send those images many, many times. So we want to get those savings many, many times. Now, I hope you are familiar with the notion of the entropy. So the notion of the entropy of a distribution, right? It's just the sum for all the states in it of the probability that the distribution, gets the state times logarithm of 1 divided by the exact same probability. And Shannon told us that this thing we cannot encode better than this. So this is the theoretically best possible thing. Now, what does this actually mean? It means that if you sample, so for the purpose of this paper, we'll talk about X as being a distribution over images. So it is not one symbol in itself, meaning like one sort of pixel, but it represents an image. So it's a distribution over the whole sequence of images. And what this tells you is you sample images with the distribution of the image, and then you encode it in such a way that this is approximately the number of bits required to send, to encode P of X given X. And this is the absolutely theoretically best. So we can't do better than this. There are many schemes which want to, in a way, get close to this. And the one that we discussed here is going to get close to this thing. Now, the details don't matter, but the point being that to encode something and reach this, you would need the distribution of the data, because you see it here. If you want to optimize this thing, you need to know what's this distribution, right? And the worse your approximated distribution of the P of X, so we will want to approximate this distribution. So this is the true one, and we want to approximate it. Now, of course, we will not approximate it perfectly, so we will incur a cost. And the closer we get to it, the better our compression will be. But the point being, a compression algorithm, it requires two things. It requires the input, so for example, an image, and it requires the probability that the distribution, what's the probability of this image? The question is why? Because then it will create a code such that if this distribution is very high, meaning the probability is high, then it will assign codes that are smaller. So the point being, for a compression algorithm, you need to know the probability distribution of the data in order to compress and decompress as well. And now, in reality, this is unknown. So our job is to learn P of X given X, P of X. So the better P of X that we approximate, let's write it here, approximate, the better it approximates the true P of X, the better our compression. So now the question is, how do you learn P of X, P of X? Now, there are a few ways that you can do that, but a very popular nowadays is to use that using a latent variable model. So you have a latent variable model. So what that means is that instead of trying to learn P of X directly, which is going to be hard, we will put a latent variable. So we will take something like a latent variable and we assume that X comes in away from Z. So think about it, this is an image, and this latent variable, which is in itself a vector, right? It's not just one number, will tell you, for example, hey, what's the brightness in the image? Is there a human in the image? Is there a dog? How much sun is in the image? How much water is in the image? Like, it tells you something about the image. So now our probability of the data, which is also called marginal probability now, we'll see why, is equal to marginalizing across all the possible Z's, but I should use an integral to make it clear that this thing is part of R. So it is P, we marginalize. So it's P of X given Z times P of Z, dz. So we marginalize across all possible latent variables and we create X. So now the whole point of this thing is that we set, and it can be a very simple distribution, right? It can be something like a normal where you take this one and you take an isotropic normal. And this one is that we want to learn is that it's easier to learn. So this one is fixed, but this one is learnable. And P of X, we could learn that as well, but we believe that that's hard to learn. And we believe that this thing is much easier to learn. So we go by a latent variable model. Now, with latent variable models, I hope you are familiar with the variational autoencoders and with the ELBO, the evidence lower bound. And the whole point is going to be that we'll need also a distribution across the latent variables. So we will learn a distribution that given X sort of learns what's the posterior distribution for the latent variable models. If you are familiar with an autoencoder, this is exactly what the encoder does. It given an X, it provides you a distribution over the latent variables. Now you are sampling one, and then you are creating one, the decoder being P of X given Z, and here you are getting like a reconstruction, which is technically a sample. Right. Now that we discussed what's a latent variable models, let's get into this scheme. So let's start with some results, and we see that here we'll see some experiments with compressing MNIST images. I know it's not the most complex data set, but the point being, this is the method that we use, and you see it gets like 5,000 bits for 30 versus like 17,000, and this is what you probably use. So, you know, it has some improvement. Now, let's see how this compression worked. We discussed about the graphical model, right? I call this Z and I call this X. I'm gonna stick to, from now on, to this convention, where this one is the image, the symbol, and this is the latent variable. And let's start to understand how compression would work in this case. So, right. So all the scheme assumes that you have access to a few things. So we have a set of requirements that we'll see how to fulfill. The key point is that an autoencoder is going to fulfill all of these, but the point is that you have a sample, you have a prior distribution from your prior. You also have a way of getting a sample. You also have, a way of getting a sample from your latent. And you also have an approximate posterior for the latent given your symbol. We have all those three. So now the easiest sort of thing that you could do is that you could sample Y according to Q of Y given S. So this is the sample that we want to encode. We sample a latent variable from it one. Now we have that sample. Then we could encode this sample using P of Y. Then we can go and encode S using P of S given Y. And now we can send S and Y. Now we need to pay a bit attention of the order. So we encode both of them. We send both of them. And the scheme that we use is INS, meaning this idea of encoding and decoding from sort of these symbols to bits. And the point is that this is stack-like structure. So when we decode, think about this as being a stack. So this was the first thing that we put in, this is the second thing that we put in. So then when we decode, we'll first look at this thing and then at the other thing. Now you notice that we encoded them differently, right? We encoded firstly Y and S, but when we send them, we put them in the reverse order. And we'll see why. So when we get to the decoder, we firstly look at Y. So we decode Y using our prior distribution. The receiver knows this prior distribution. We tell it beforehand. And now because we have that, we can decode S using P of S given Y. If we were trying to firstly decode S using this distribution, it would have not worked because we didn't already know the Y. We needed to decode first the Y in order to be able to, make this conditional distribution. So that's why we send them in the reverse order. So now that you have decoded both Y and both S, you basically got back your S, which is the thing that we care about. This one was just an auxiliary factor in order to learn better distributions. So this is the encoding process. And let's think about how many bits we used. So here to encode it, we use approximately minus logarithm P of Y. This comes from the entropy, the information theory knowledge, right? It's the it's basically the logarithm of 1 over P of Y, which if you translate it gives you minus that. So this is how many bits we'll need on average to send a Y. Now given a Y, this thing is going to take minus logarithm of that thing. So it's minus logarithm P of S given Y. And we needed this many bits to send. And this is perfectly fine, but now the point in everything is that we can do better than that. We can save some bits, and we are going to save, right, exactly logarithm of Q of Y given S. Now the question is how? How are we going to do that? So we'll still incur the cost to send these two things, but in the cost of sending these, we'll also send some additional bits that we will not need to send after that. I know it's hard to wrap your head around it. It was for me as well, but let's look at it. So here we assume that this is random sampling. You assume that you pick, how do you do random sampling? And we look at it. So let's say that we take a distribution, we take Q of S, and we need to discretize it because when we train, for example, an auto-encoder, this thing is going to be continuous. But when we work with compression, we can't compress, real numbers. We need to discretize. So we are going to discretize it, but we are going to pay a small price for that. But the point is that we discretize. So now our distribution, if you look into the CDF of the discretized version, it's going to be just the CDF. So it's going to be between 0 and 1. And let's say that we have just 4 types of we have a latent variable, which is a scalar, and it can have 4 possible values. Now this applies to multiple dimensions, but doesn't matter for our purpose. So it's the CDF, so it's between 0 and 1. Now, you know that you can sample by using the inverse CDF. So if you pick a random point in here, for example here, and then you go to the CDF and down, you sample the Y3. Now, so you use a uniform random to sample from it, and you go down. And this is how we sample. Now, the key observation is that sampling from a uniform can be achieved using a binary sequence. So let's say that we have the binary sequence 0, 1, 0, 0, 1. And we are going to iterate like this, and we'll see how picking one such random sequence simulates sampling from a uniform. So we take the interval from 0 to 1. We always split it into 2. Now, if it's 0, we keep our next interval as being this one. If it's 1, it would be the other one. So here we got a 0, right? We look there. Now, I'm going to cut my 0. Now I look at 1, so I need to look here, and I am looking into this new interval. I cut that as well. I have a 0, so in this new interval, I'm going to look into this bit. Right? We are making our interval smaller and smaller. Now I have a 0, so in this interval, I am going to look again at 0. And finally, we have a 1. So in this interval, we look just at the one at the top. So now we got to an interval. And you see, if you map that interval back to this inverse CDF, we touch this one. So we essentially sampled a Y2. So the point is that we simulate sampling using a sequence of random bits. Right. So now we simulate sampling, but the point being, if we give this sequence of random bits, so it's still random, but we sample it somehow, and we use it to encode, we can use this thing to decode as well. How? So this whole thing that we showed here, you can see it in a different way as binary tree, right? You can see it as, so here you have the whole interval 0, 1, and here you have the interval 0, 1 over 2. Here you have 1 over 2, 1. And let's say that here you are going to have the interval 1 over 4, 1 over 2. It's in this one. So now, when we got to let's say, to get to this interval, you need to make a 0 and then need to make a 1. And you send that. But if you already know that you reached this point, you can go back and retrieve the sequence. So you can go back, you know that the last one was a 1, and then you can go back again, and you know that this one was a 0. So the point being, if I provide this sequence to this mechanism, I'm able to get it back. And that's what we are going to do. So instead of random sampling by just randomly sample, we'll sample using our provided random sequence of bits. So now this is something like a pseudo sampling. It's still sampling. We still sample from this distribution. It's still, we want it to be random, but something like, in a way, the seed of this, but it's not the seed, it's just a sequence to simulate uniform sampling. We provide that. So if we provide it, we'll be able to get it as well back. So assuming now that we provide that random sequence of bits, we can sample from it. If we sample from it, then we retrieve back, sending this Y requires the information that we store in Y due to sampling this way is going to be equal to its probability of log or minus log of probability. This has to do with the fact that if you think of it as a Huffman encoding, which is similar to this binary tree, Huffman encoding simulates best entropy encoding, which basically gives that the number of bits needed to send this symbol is minus log of this thing. So now I understand it can be a bit complicated, but the key point is that by using this mechanism and then the receiver using it to decode Y, it can get back this many bits. It can retrieve them. So because the receiver also retrieves this many number of bits, then we've essentially sent more information than just what we physically sent. So this is still what we send, but Y can be used in this smart way at the bottom in order to obtain more bits. And this is the bits back coding mechanism. But how is it actually implemented? So the first thing is to notice, to look at what we said and see that it's similar, identical to an autoencoder. So the number of bits that we'll send is that we send this number of bits to encode Y. We send this number of bits to encode our actual image, and we'll get back this once. So we are sending additional information without any cost using that scheme. And this, of course, needs to be averaged across the posterior of the latent because we do sampling here, remember? And if you do a bit of manipulation, this is exactly minus the ELBO. So this is the number of bits that we need to send. This is the message length. And the message length, it's the same as the ELBO. So you want to minimize the message length, so you want to maximize the ELBO. And maximizing the ELBO, it's exactly what you do in a VAE. So this is a way of training this model. But let's look a bit how saving the bits would work with this bits back and with INS. So we discussed that we have a stack-like structure. So we wanted to send this before, for example, let this be an X1 that we wanted to send. No, let me use the same thing. So let this be an S1 and let this be a Y1, right, that we wanted to send. Now we do as follows. Extra information. So this is information that we want to send as well. And now we focus on this image that we want to send. The first thing is that So we haven't yet sent this information. It's still on the sender to send it, to encode it. This represents a sequence of bits. These are bits. We think of them as being random bits. Now, we take some of these random bits that are there. We take exactly this many number of bits, and we use them together with the mechanism that we explained here with picking a sequence of bits using the CDF in order to sample from the posterior. So we use this sequence of bits in order to sample. So now in this one, we technically encoded some bits, those that we used for sampling. So now if we send this thing, we will be able to get back those bits. Now we will encode the image, we put it on the stack. We encode the latent variable, we put it on the stack. And now the number of things that we need to send is equivalent to this thing. So then when you go and when you decode, you firstly decode this thing. You then decode this thing. And now you will have your Y0 that you have decoded. And now you go back and you obtain the sequence of bits that you have used it initially to encode it. So you take those and you put the bits back as well. The whole point being that these bits that were there, they are not sent, or better said, they are sent implicitly using this Y0. So we save them. We put the actual bits that we send are for encoding this one and encoding this one. And when we encode this, we get more bits by not technically directly sampling from this one, but using a sequence of random bits. Now, there are some issues that could affect this thing because this random sequence of bits, it's not technically random. It's, to be fully specific, part of the latent encoding of the latent variable of the previous one, which was encoded uses the prior. But these are details because in their experiments they didn't seem this to be a problem. So for the purpose of this general area, you can assume that these are random. And that's it. Now, one thing that you need to take care of, and I'll just mention it without going into details, is that the distributions P of y and Q of y given S, they need to be discrete. But when you train an autoencoder, these are normal distributions. So these are continuous. So you need a way to discretize them using a way that you want to discretize. Now, the way that they discretize it is that they pick the random normals, these normals, right? This is the prior. And they made bins of equal mass. So the area under this bin and the area under this bin are the same. Why? Because this is a maximum entropy discretization, so it preserves the most amount of information into the sample. So if you take two samples from here and there, if you are making this to be a bin, then the samples would be the same. So you would sort of lose information. But if you make the bins differently based on the areas under the bin to be equal, then it's most information is preserved. So now we discussed how the bit stack work. We also discussed that optimizing this is identical, equal. It's not approximate, it's equal to maximizing the ELBO. And now let's see what they've got here. So they used a very simple VAE model with basically two layers, right? An encoder of 100 and then a latent of 40. Very simple model, and they've got good results. So they've beat everything else, not by a large margin, but they've beat. The whole point from this table is that the beats back approximates basically identically the ELBO. So this means that the approximation is good, and there are not many issues with the random bits sort of not being random. And this also shows that the posterior is well approximated here, but let's not get into those details. That's all for this paper. I hope you enjoyed. I was, fascinated by this bits back coding. I think it's honestly a novel idea. I saw that Hinton worked with those things in the 90s, but to me it was a novel idea. I'm gonna link the paper and also an article which explains these ideas in more detail. Thank you for watching. See you in the next one.